So far we have seen the different functionalities which basically add the new value at the end of the single linked list, and which will basically add and remove the new values in front of the single linked list, right? And we have also implemented get functionality on a single linked list. Now that combining all these functionalities, we can write the insert operation on a singly linked list. So insert operation, what exactly it does is, it is basically used for inserting a new value anywhere in the singly linked list. For that operation, what exactly we will do is, we will basically take the index from the user and will also take the value that user wants to insert into the singly linked list. So here our job is to make sure that we are inserting a new node with the value that user has passed at the given index. So that is the main aim of the insert operation on a singly linked list. So remember that we have to take the index and we have to take the value, and we have to make sure that the new node with whatever the value that user has passed, we have to make sure that we are inserting a new node at the index that user has passed. So obviously, just like any other operation that involves index, right? The possible ranges for the index are basically, in the case of single linked list, are from 0 to length of the single linked list minus 1. But here there is a catch. The valid index for insert operation is from 0 till length of the linked list. Why? Because if you consider the single linked list that we have here, right, the indexes are 0, 1, 2, 3, 4, 5. But inside this single linked list, we almost have 6 values. That means the valid indexes are from 0 to 5. But the thing is, if the user passes an index 6, right, that means that we can insert a new node at the end of the singly linked list. That's why for insert operation, the possible range of index that user can pass is actually from 0 till the length of the linked list. And obviously, since singly linked list can store any type of the value in it, there will not be any validations on the value that user is passing. So the only validation that we have to make sure is if the index that user is passing is in the range of 0 to length of the linked list or not. Okay, so that is the basic definition of a insert operation. Now let's go ahead and let's try to understand what are the different cases that could arise when I try to implement the insert operation, and what are the functionalities that we can reuse for implementing the insert operation. So the first check would obviously be to check if the index that user has passed is invalid index or not. That means that when we are taking the index from the user, right, index is nothing but an integer value. So user can pass any negative values, and user can pass values that are greater than the length of the singly linked list. Obviously, in those cases, we will not be able to insert a new node into the singly linked list, right? That's why, as part of the first check, we will basically check if the index that user has passed, if it is less than 0, or if the index that user has passed is greater than the length of the linked list. If this is the case, we will simply return false, indicating that we are not able to insert the new node into the singly linked list. That is the first case. So besides this invalid case, all other indexes whatever we get from the user are basically valid cases, right? Out of those valid scenarios, the first scenario is if the index is equal to 0, right? The whatever the index that we are getting from the user is 0. That means that we already have a value at index 0. That means that when user asked us to perform insert operation at index 0, user is literally telling us that, insert a node before the existing head node, right? That operation is nothing but unshift operation, right? So we have already implemented this unshift operation, and we tried implementing it in such a way that it will handle all the scenarios already. That's why if the index is passed by the user is 0, what we will do, we will simply call the unshift operation with whatever the value that user has passed. So it will make sure that it is inserting a new node at 0th index. 0th index is nothing but before the existing head of the singly linked list. Let's assume that the value that user has passed is 10, right? So in that, let's say, again, let's assume 10 only. Now, unshift operation will make sure that it is inserting a new node, and head node also will get updated to the newly added node. So that is the first scenario when the index that is given by the user is 0. And as part of the third case, basically it is the second case where, let's say, the index that is given by the user is equal to the length of the linked list. That means that the last node is at the index length of the linked list minus 1, but the index that is given by the user is equal to length of the linked list. That means that we have to insert a new node after the tail node. That is nothing but a push operation that we have already implemented. In that case, if the index is equal to length of the linked list, what we will do, we will simply call the push functionality with the value that user has given. Let's assume that the value that user has given is, let's say, 1000 or 100, right? In that case, what exactly we will do, we will simply create a new node with value 1000, and we will adjust the next pointers of the current tail node, and we will update the tail node to the newly added node. Now if you see here, the index of the value 1000 will be 6. Okay, because we altogether have 7 values inside the single linked list, and the value 1000 is at the index 6. That's why you have to make sure that you are taking the valid values of the index from 0 till the length of the linked list. Okay, so that is the second scenario when the user, whatever the index that user has given, is the last index of the singly linked list. Now let's just try to understand if the index is any other index than 0th index, or the index that is equal to length of the linked list. That means that user wants to insert a new node with whatever the value after the index 0 and before the very last node we have on the singly linked list. So in that case, what exactly we will do is, we will try to reuse the functionality of the get functionality. But before I go ahead and I explain you the algorithm, right, let's just try to understand how the insertion actually happens. Let's assume that we have, let's say, 4 nodes inside our singly linked list. So the index will be 0, 1, 2, 3. Let's say the values are 10, A, C, let's say D are the values we have inside the singly linked list. And we have the head node and we have the tail node, and each and every node is connected to the next node like we have inside the singly linked list. Now here, as part of the insert operation, what I have actually given is, I want to insert a value at the index 2 by the value AB. That means that right now the index 2 has the value C, right? Now we have to make sure at the index 2 we are inserting a new node AB. That doesn't mean that we actually have to update it. We may have to make sure that we are inserting a new node altogether. That's why what exactly we will do is, with whatever the value that user has given, right, we will create the new node, and this node should be available in its before node, right? That means since we are inserting a node at second index, this node's reference should be available at the node that is at index 1. That means that next of A should store the reference of AB. Similarly, the next of AB should store the reference of C. In this way, this connection will be broken and new connections are being established. As a result, this AB will be available at index 2 and C will be available at index 3 and D will be available at index 4. So what exactly you have to observe here is, to insert a new node, first we have to have the nodes that are available at index 1 and the node that was at index 2 before we inserted the node, so that to the newly created node we can adjust the connections. If we generalize this, right, let's say if I am trying to insert the node at kth position, we have to have the node that is available at k-1th position and kth position, so that whatever the new node that we are inserting, we can adjust the next and next of the next nodes clearly. So in this way, to reuse the already implemented functionalities, what exactly we will do is, to have the access of this k-1th node, we will try to reuse the get functionality. Once we get that k-1th node, we will have the kth node also by simply doing dot next of k-1th node, and we will have a newly created node, and we can simply adjust the next pointers very easily. So that is the algorithm that you can use when the index that is given by the user is anywhere after index 0 and before the length of the linked list -1. So that is the otherwise index is greater than 0 and length of linked list. If this is the case, what we will do, first we will get the k-1th node. Once we get the k-1th node, this is k-1th node. Now the kth node will be this k-1th node dot next, right? Now with whatever the value that user has passed, we will create new node to it. Now this k-1th node next should be this new node that we have created. That's why k-1th node dot next will be equal to new node. Now we have adjusted the connection for the newly created node. Now to this newly created node, the next should be whatever the kth node that we had previously, which is available inside this kth node variable. That's why to update the next, new node dot next is equal to kth node. In this way, we are actually inserting the new node into the singly linked list. Just remember that this is not the update operation. We will have to insert a new node into the singly linked list. At the same time, we have to make sure that none of the values are getting lost while performing the insert operation. So for that simple operation is, these are the different cases, but this is the specific case where user is trying to insert a new node after index 0 and before the length of the linked list, whatever the index that user can pass. Okay, so that is the normal algorithm for insert operation. So for that, let me just define an insert function. Okay, this insert function basically will take the index at which we want to insert the new node, and it will also take the value which we want to use or store as part of the node that we are trying to insert at the index. Now, as part of the index operation, the possible range for the indexes are basically from 0 till the length of the linked list. Don't forget this, because we already have the values from 0 till the length of the linked list -1. So we can add a new node at the index that is equal to the length of the linked list. So whatever the index value that user is passing for this insert operation still could be a invalid value. How? The user can pass any negative value, or the user can pass the value which is greater than the length of the linked list. So we can't do, or we can't insert a new node in those cases. So what we will do in those cases, we will simply return false in such cases. So first what I will do, we will simply check if index is less than 0 or if the index is greater than the length of the linked list, that is this dot length. In these cases, we will not be able to insert a new node into the singly linked list, so we will simply return false, indicating that we haven't inserted the new node at the index that you have passed. If this is not the case, the other case is whatever the index that user has passed is 0. That means we already have a head node at index 0, but we still want to insert a new node before that. That means at index 0 itself, I want to create a new node. That operation itself is like inserting a new node in front of the existing head node, which is nothing but unshift operation. So if the index is 0, then we will reuse this dot unshift with the value that user has passed. Since we are able to insert the new node here, we will simply return true in this case. Okay, so what we did, if the index is 0, that means that we are adding a new node in front of the existing head node itself. That is nothing but unshift operation. So we reuse that function that we have already defined earlier. Now, if this is not the case, the other case is, let's assume that whatever the index that I have passed is equal to the length of the linked list. That means from 0 till length of the linked list minus 1, I already have the values. So the last node, which is at index length of the linked list minus 1, is tail node. So I'm trying to insert a new node at, that is equal to the length of the linked list after the existing tail node. That is nothing but a push operation. So in that case, if this index equal to this dot length, in this case I will simply reuse the push operation with the value that user passed. So in that case I'll simply return true. Okay, apart, if none of these conditions match, that means if the index is not matching with any of these cases, then we are trying to insert a new node anywhere after index 0 and before the length of the linked list minus 1. That means after the head node and before the tail value. So to insert this, here also we will reuse one of the functionality that we have already written. How is, let's assume that I want to insert the node at 5th position. In that case, let's assume that the linked list also has a total of 8 nodes. In that case, if I have to insert the node at 5th position, I have to go till 4th position. The node at the 4th position first I should get, and I should store the remaining nodes in some other variable, and I need to insert the new node, and I need to make sure that I'm adjusting the next pointers clearly, so that we are having no abnormal behavior in the singly linked list that we are implementing. So to do so, what I will do is, first I will create a new node. Const new node equal to, let's create a new node with the value that I want to insert. Okay, now let me just read the node at the index minus 1. That is by using the get functionality. So first what I will do, I will call the index minus 1th position. So I've got the node that is at index minus 1th position available inside the node. Now let me just store the next nodes that are available after index minus 1th position, that is from the index till the tail node in some variable, so that in the later we can adjust the next pointers. So for that, let me just read. I'll simply name it as next nodes equal to whatever the node that we have dot next. Okay, so this node we've got, from the next will basically give the next node from the index minus 1th position. Now all we have to do, we have to insert the new node at the index, that is after this node that we have read. So what we will simply do is node dot next equal to new node that we have created. Okay, but to this new node we have to add the next nodes that are available. For that, what we will do, this new node dot next, we will assign it to next nodes. Okay, so we have inserted the new node, we have adjusted the next of index minus 1th node with the new node that we have created. To the new node we have adjusted the next nodes. In that way we are inserting the new node at the index that user has passed. Here we are basically inserting a new node, right? That means that length should be incremented by 1. This dot length equal to this dot length plus 1, and we will simply return true, indicating that we are able to insert. If you see here, in the previous cases we are calling the already implemented functions which are taking care of length, but here we are inserting the node manually. That's why I'm incrementing the length by 1. Now we have written the logic for supporting all the cases of the index that could appear. Okay, this is the implementation of insert operation. Now let's try to perform the insert operation and validate the results. So if I just modify this set call to insert call, here I'm passing a negative index, which is not a valid index. So before traverse and after traverse should have the same result set, because we are not inserting the new node. So if I simply execute node singly linked list.js, just see the output here. Here the result is 10 codingpal.org true and 10.134. The output after inserting also, we have executed we've got the same thing. Okay, which is same as the values we have in the input linked list. Okay, if we pass any positive invalid value also, you should see the same result. Okay, so the largest possible value for the index is basically equal to the length of the linked list. So in our case, the length is 4, right? So the existing range of indexes is from 0 to 3. If I pass 4, ideally it should insert a new node after 10.134. So the tail node will be Sai, because we will be reusing this push functionality in the insert operation. So if I execute it, you should see the same thing. Head is before inserting, this is the result set. After inserting, this is the result set. If you see here, since we are inserting after the tail node, that is nothing but the new tail will be with the node that has value SAI. Okay. Similarly, you can pass any index. Let's say I want to pass an index 0. That is nothing but unshift operation it's going to use. So head node will be node with SAI. So if you see here, the same thing is getting reflected. Okay, and you can pass any value that is anywhere in between, after head node and before tail node. So let's say I want to insert the node at index 2. That means right now index 0 has 10, index 1 has codingpal.arg. If we insert it index 2 with the node value Sai, after codingpal.arg, I should get a value of Sai after the true and 10.134. If I execute it, I got the same result as I mentioned. Okay, this is how we basically perform the insert operation on a single linked list using JavaScript. Okay, now that we have implemented the insert operation, let's just try to analyze the time complexity and space complexity of the algorithm that we are following for inserting a new node into the singly linked list at a given position by the user with whatever the value that user has passed. And this also, let's just try to divide and analyze in best case as well as worst case. Okay, so when will the best case of insertion operation will occur? Let's assume that we have some number of nodes that are available inside the singly linked list. So as part of the best case is something that it will simply occur with a simple update operation. So in the case of insert operation, whenever the user is trying to insert a new node in front of the existing head node, that means that at the index 0 itself, that is a simple update operation because we already have the head node. We are simply using a unshift operation performing the same insert. Similarly, if the user, whatever the index that user is passing, if it is the index that is equal to length of the linked list, in that case we are simply reusing the push functionality. In these two scenarios, since we had the access to the head node and tail node, with the simple update operations, we were able to add the new node into the singly linked list. As a result, that is the best case of a insert operation on a singly linked list. In that case, obviously both unshift as well as push operations will take only constant amount of time. So we can say in the best case scenario, the time complexity will be order of 1. Now, when will the actual worst case scenario of the push functionality insert operation will actually occur? Let's assume that we have some number of nodes available inside the singly linked list. Here, let's assume that there are n number of nodes. So this is the head node and this is the tail node, index 0, 1, 2, 3. Now, just assume that this is the nth node. Now, let's assume that whatever the index that user has passed, right, if it is equal to the n minus 1. So we already have the n nodes available in the singly linked list and the index that user has passed is n minus 1. That means that user wants to insert the node at the very last index in the singly linked list. In that case, we have to call the get functionality by n minus 2, right? In that case, get function to get the node that is at n minus 2th index, we have to run a loop for n minus 2 number of times. So in that case, that's why the worst case time complexity will be order of n minus 2. We can simply say order of n. Now let's just try to understand the same thing in terms of space. So if you already know when is the best case, right? When the user is trying to insert the node at the beginning or at the end of the single linked list, that is the best case scenario. In both those scenarios, we will simply reuse the unshift and push operations, which will basically make the necessary adjustments in a constant amount of memory. If you remember the time and space complexities that were involved in the push and unshift operations, right? They were constant. As a result, in the best case scenario, the space complexity will be order of 1 only. Now let's just try to understand the space complexity involved in the worst case scenario. Here altogether we are calling the insert operation at the index n minus 1, right? And we are making the reuse of the get functionality. And if you remember the time complexities and space complexities involved in the get functionality, right? We will simply reuse a single variable for reaching the node at any position in the singly linked list. As a result, even in the worst case, the get functionality will have a space complexity of order of 1 only. And once we get the node also, after that all we are making two next pointer adjustments, right? And these next pointer adjustments will obviously be a simple assignment operations, and they will take only constant amount of memory. As a result, the overall space complexity in the worst case scenario of insert operation on a singly linked list where you are trying to insert the node at the very last index will be order of 1 only, even in the worst case scenario. Okay, so that is the time complexity and space complexity analysis of a insert operation on a singly linked list.